So today I will present a publication that I was working on, submitted to the or accepted by the IEEE Intelligent Conference on Intelligent Transportation Systems. Now, the intended audience are people with previous machine learning background, but are unfamiliar with perimeter control. So work was done jointly with the PhD Xiao Tan Li, but as second author, I still made critical theoretical contributions towards the design of the paper to make it publishable. So here's a brief outline. The presentation is about 15 minutes long, and at the end, there's about 5 minutes left for questions. So first, to get on the same page, what is perimeter control? Well, perimeter control is a type of large-scale traffic control problem where we control the number of vehicles entering or exiting a region, trying to maximize some sort of objective function, which is typically the total travel time of all road users. So I'm sure we're all familiar with small-scale traffic control, which is a type is traffic signal control, where we control the number of vehicles entering or exiting specific links. Here, optimal policies focus on small-scale local characteristics such as green wave synchronization or having flow proportional to pressure. Perimeter control is a large-scale type of traffic control. So here we're concerned with more large-scale characteristics, such as the density of the entire regions or MFD theory. So the method we use is reinforcement learning. So reinforcement learning is a relatively new algorithm compared to the transportation domain. And often what they do is they take these new algorithms and they perform an analysis of how they do on the existing problems, which is very similar to what we want to do. Some terminology you might want to know is, first of all, the Markov decision process, basically a way to take a problem from from a humanistic standpoint into a format that a machine can easily learn or interact with. For example, you discretize a space, specify the rewards, action space, state space. Neural networks are relatively newer algorithm. So it's a function that has the ability to learn complex patterns between the inputs and the outputs. So when we combine neural networks with the Markov decision process, what we're basically hoping for is for our algorithm to learn relationships or learn optimal policy that humans themselves cannot think of. So unlike supervised learning, where we have specific input and outputs, specific predefined optimal outputs for inputs, reinforcement learning is a decision maker. So we do not necessarily know what the optimal actions are for each input state. Rather, we have a reward signal and it tries to maximize that reward signal. So the specific type of RL we want to use is model free. So model free is basically don't use a model, but what is the model? Model-based reinforcement learning is when instead of interacting with the environment, the agent interacts with a simplified version of the environment, which can either allow the agent to learn faster, or sometimes we can even derive a closed form solution for the optimal policy. In perimeter control, the models that's typically used is called the MFD diagram. So you collapse the entire region into a single statistic, which is the inner density. And then the MFD would try to estimate how much flow you would get out of that inner density. So basically, it's kind of type of efficiency rating, and you want to maximize the amount of flow, obviously. So basically the motivation, as we said, is just to perform an analysis of reinforcement learning on this older perimeter control problem. And our contribution is we're the first to apply RL and perimeter control at such a high level of detail. So we're both model free and we're doing microscopic, which simulates individual cars. And second, we provide insights into the policy, which can be used by other people to design similar controllers or to design a similar controller or contribute to the field. So previous works can basically be classified into non-RL based and RL based. So for non-RL based, it's dominated by MPC and PI control. So there's drawbacks to these two types of control. For example, model predictive control, MPC, basically searches for the optimal policy within the policy space. And because this can be so high dimensional, what you need is a simplified model of the environment so it can actually finish its search in a reasonable amount of time. And obviously, obvious drawback is the cross simplification you're gonna put in that model. PI control is a type of controller which attempts to keep some sort of reference signal in your simulation to a human defined level. So drawbacks in there include humans have to define the reference signal, they have to define the proportional and integral terms, so there's a lot of room for human error. So before papers that try to use reinforcement learning on perimeter control, there are a few, but they tend to cover different domains. For example, there's one that does it on the macroscopic level, which is a gross simplification, and there's others that try to redistribute previous total inflow rates. So this comes from MPC and PI, and obviously suffers from what I just mentioned. So here's our experimental setup. On the left side, you see we have our protected region, which is a single region for simplicity and is meant to replicate a downtown inner core. On the right side, you see our traffic demand, which is meant to replicate a rush hour. Here's how we define a Markov decision process. So our state space include mostly three different types of information: the inner density, the density on feeder links, and the future demand that's coming in the future. Our action space is a single flow rate for all the gates on the perimeter, and the reward, transition dynamics, and discount factor are also described in this slide. For the specific type of RL algorithm we use, we went with proximal policy optimization. This is basically a state-of-the-art new algorithm that is compatible with continuous action spaces, which also learns online, a policy gradient, which is also policy gradient. So we're not redesigning these RL algorithms. We won't go too into depth about them, but on the right, we have a summary of the hyperparameters we use for reproducibility. So results and discussion. So now to the results. So first we will compare the different state space designs. So here on the table, you can see different state space we use, progressing from not much information towards adding more and more information, with the bottom row including the densities and the future demand. So as we see, including more information led to better performance, and we will now try to intuitively understand how. On the right figure, you have the policy visualized for our one-dimensional state space. The darker lines represent the more recent times, and as you can see, the algorithm converged to a relatively simple three piecewise linear function. So if density is less than a certain threshold, it will allow many vehicles to enter. In between these two thresholds, it will use a linear relationship with decreasing density proportional to how congested the region is. And finally, when the region is over congested, it will settle for this minimum inflow rate, which is very intuitive. Our four-dimensional state actually converges to a similar piecewise function, but what you are seeing is actually as future demand increases, or as we predict more cars to arrive at the network, the policy chooses a more and more conservative piecewise linear function. So basically shifting it more and more to the left. From a human perspective, we can understand this as we use a negative relationship between the the density of our inner region and the flow rate, but we're anticipating the future conditions and preemptively adjusting our policy to match what the conditions will be in the future. So now that we kind of understand how our RL could have used the more information to getting better, we will look at how our RL compared to our baseline, which is the PI control. So without going into too much details, we basically utilize a PI adaptation from another previous work on perimeter control. It will try to keep inner density near a human set level, which should be the set point of the MFD. The PI and the proportional and the integral terms actually solved closed loop to arrive at the set point without any fluctuation, so deadbeat behavior. This was done with a simplified model of the environment to obtain the closed loop solution. So on this table, we can see how our PPO compared to our PI baseline, also no perimeter control. So I think we should notice two things. First of all is that our both controllers managed to beat the no control case significantly. Now this is expected. The second thing we should notice is that the RL controller beat the PI controller, but consistently, but not by a significant margin. So here towards our first observation, we can see that how did the controllers beat the no control case? Well, they did basically the very intuitive thing and kept the inner density near the optimal as defined by the MFD, which we see in the left diagram. On the right diagram, we can see that as an unfortunate consequence, many vehicles are held up outside the protected region due to the due to restricting the inflow, and the effects of this spillback use is left for future works. So it's clear how the controllers beat the no control case, but how did RL beat the PI case? On the figure on the left, you can see the action rate over time. So one thing we notice right away is that the green action rate, which is the PI controller, is fluctuating. So obviously the PI controller is oversensitive, and it's likely due to the fact that the parameters, the PI constants, are set deterministically and they're not learning based. On the right side, what you're looking at is a diagram of the inner density over time, and then on the right is a diagram of the trip completion rate over time. So on the middle, we see that RL actually holds a lower inner density than the PI controller. On the right side, we see that this lower density is actually slightly more optimal, which has a slightly higher flow rate. Again, this is not surprising because PI has its reference point deterministically set, and inaccuracies in the model can lead to improperly set reference points, while RL is iterative and self-learning, so eventually it will adjust itself to converge towards optimality, although it did not beat PI by a significant margin. Finally, to make sure our controller learned something useful and did not overfit, we performed generalizability tests. So we test its ability to generalize to the same network, but for example, we scale up the demand or we change the shape of the demand profile. And from the figures, we see that our RL controller was able to maintain its gains on both baselines under a great variety of scenarios. So what did we learn from all of this? Or what is our contribution? Well, we successfully formulated our perimeter control process into an MDP format and applied reinforcement learning, and were able to match and beat the standard baselines. And secondly, we provided an analysis of the policy to intuitively understand what our controllers were doing and how they can be improved. For example, providing information on the future demand allows the controller to act preemptively on the for the future conditions in anticipation of the future conditions. And secondly, it seems like a relatively simple policy can obtain good results. So in suggestion, perhaps a well-crafted human rule-based controller can be very competitive and also not suffer some of the drawbacks that RL has, such as the black boxes of its neural network, which leads to a lot of reliability issues. So for future works, we think that reinforcement learning might better benefit from scenarios with more complexity, where RL is designed to find policies that humans cannot think of themselves. So for example, these include multi-regional perimeter control. So you would have multiple competing MFDs, heterogeneous perimeter control flow rates with multiple flow rates around the spatial locations of the protected region. This will handle things like heterogeneous or unsymmetrical network properties or unsymmetrical congestion, or ways to make the actual learning algorithm learn faster. Another area to look at is the actual models used in perimeter control. So right now it's dominated by the MFD diagram, which is a gross simplification of a large traffic network. And on the figure on the right, you can see that clearly there's a lot of noise and it's not a one-to-one mapping between density and production. So it's worth investigating under what circumstances does the MFD model break down, and how can we capitalize on this on improving the accuracy of our model, or capitalize on the areas where the MFD is inaccurate with the intention of creating more effective controllers. So basically, what additional information do we need to feed our controllers to not be negatively affected by the MFD breaking down? And this is the end of my presentation. Here are my references.